so welcome to the course Nature and Properties of Materials. Today in week 8 we'll talk about non-mechanical properties and laboratory demonstrations. So this course is offered by Professor Vishak Bhattacharya, Department of Mechanical Engineering, IIT Kanpur, and I am TA Alka Janget from IIT Kanpur. So firstly we'll be going through some sample assignment questions which will help you in solving your weekly assignments, and then we'll go through some lecture notes. So first question is, which material is not diamagnetic? So this question is related to magnetic properties. So your options are iron, gold, tin and mercury. So your answer will be iron, because iron is ferromagnetic material. It shows higher magnetism compared to these other materials. So in case of diamagnetic materials, you have these magnetic materials which align against the magnetic field, which are known as diamagnetic materials, and the magnetic susceptibility chi is lesser than 0, which means it is always negative value for diamagnetic material. And these materials are repelled by the magnets and move from a stronger to weaker field, and these materials are independent of temperature. And these materials magnetize in the opposite direction. They do have a small amount of magnetization intensity compared to other materials, and gold, tin, mercury, water are some examples of diamagnetic materials, and these have constant relative permeability. Next question is, piezoelectricity is shown by substance which are, your options are polar, non-polar, symmetric or asymmetric. So piezoelectric we also studied in case of your smart materials. In that I told that some materials which have asymmetric distribution of charges, so on application of some stress they might show some redistribution of charges, showing some polarization. So answer will be asymmetric. So piezoelectric materials have an asymmetric distribution of charges which gives them this type of effect. For example, in case of quartz, you see this type of structure. So here your silicon atoms and oxygen atoms are distributed in this manner. So as you apply tension or compression type of forces, you'll see the distribution of charges will change, and in this case you can see two positive atoms are here. So this side becomes positive, and in this side you have only one positive and two negative. So this side has negative ions. So this will be reversed in case of compression. Next question is, which material shows less permeability? So your options are ferromagnetic, paramagnetic, diamagnetic and ferrimagnetic. So you have to find out which shows least permeability out of these four options. So in case of diamagnetic materials, they have lesser permeability compared to these three. Now the magnetic permeability of a material is its ability to acquire magnetism when it is exposed to a magnetic field, and it is the maximum of ferromagnetic materials. And which are examples of ferromagnetic will be your iron, nickel, cobalt and these type of materials. The magnetic permeability of diamagnetic materials is less than the permeability of vacuum, and paramagnetic materials show better permeability than diamagnetic materials. Which of the following materials is considered as the non-magnetic material? Options are diamagnetic, ferromagnetic, ferrimagnetic and anti-ferrimagnetic material. So your answer will be diamagnetic. So ferromagnetic, ferrimagnetic, these will have some domains which will be aligned. In anti-ferrimagnetic also some domains will get cancelled out, which will make it anti-ferrimagnetic, but when you will be applying some outside magnetic field, it will show some response. So in explanation you can see that here in case of ferromagnetic and ferrimagnetic materials, even without application of any magnetic field, you will be having aligned domains, and when you apply magnetic field, it will strongly get aligned in that direction. And if you have paramagnetic type of material, then in absence of magnetic field, it will show randomly oriented domains, and then when you apply magnetic field, it will get aligned. While in case of diamagnetic, you don't have any kind of domains, and when you apply some magnetic field, it tries to move to the weaker side of the magnetic field, so it opposes the magnetic field. So magnetic field repels diamagnetic materials because it induces a magnetic field that is directed in the opposing direction from that which is applied, producing a repelling force. And diamagnetic substances are those substances which in their normal states have no magnetic moment at all, and the magnetic permeability of diamagnetic materials is less than the permeability of vacuum. Examples will be bismuth, copper, gold, mercury, water, alcohol and hydrogen. Next question is, a certain amount of current flows through a ring shaped coil with fixed number of turns. How does the magnetic induction B varies inside the coil if an iron core is threaded into coil without dimensional change of the coil? So in case of transformers as well, you might have studied about the existence of iron core or some core. So your options are this. Okay, so magnetic induction decreases or increases or remains same, or it first increases and then decreases depending on the depth of iron insertion. So your answer will be it increases. So the main objective of these iron cores is to increase this magnetic induction. An iron core inductor is a type of inductor that uses iron or ferromagnetic material as the core at the center of its coil, and the use of the iron core is in an inductor allows for a higher inductance value, as the iron core provides a greater magnetic field than other materials like air or a ferrite core. Next question is related to optical properties of materials. So in this case, if the material has a refractive index 3 and light is falling normal from a glass sheet of the refractive index 1.8, then find the reflectivity of material. Options are 0.01, 0.03, 0.06 or 0.09. So there is a simple formula for reflectivity of material. R equals to N2 minus N1 upon N2 plus N1 whole square. So if the light is normal or perpendicular to the interface, then this formula you can use. Here N2 and N1 are the refractive indexes of two different surfaces. So N2 is your refractive index of the material, and the second one is for glass. So 3 minus 1.8 divided by 3 plus 1.8. So it will become 1 upon 4 whole square, and its value will be around 0.25. So it is written as 1 upon 4. whole square, then its answer will be 0.0625, and here you can choose this answer is the closest 0.06. So this will be the reflectivity of the material. Next question is electrical resistivity of metal blank if temperature increases. So this is related to the electrical properties of materials. So in that case, if you increase the temperature, your electrical resistivity of metal either increases, decreases, remains constant, or increases depending on the melting temperature of metal. So the answer will be increases. So you have to particularly remember whether it's asking resistivity or conductivity, because these are inversely proportional to each other, resistivity and the conductivity. So in case of metals, you can see here from plot as well, as the temperature keeps on increasing. For iron, aluminum, copper and all other metals, your resistivity will increase, because electrical conductivity comes from the electron transfer from one end to the other end in metals. So there is electron cloud that is present in metals. So if you are applying any voltage, so there will be electricity flow. So if you are increasing temperature, what will happen? There will be vibrations and collisions between these free electrons. So this will lead to decrease in the final output that you are getting in form of current. So the electrical conductivity of metals decreases with an increase in temperature, and it is due to an increase in the collision between free electrons, thereby increasing resistance. It is the reverse of semiconductors, for which conductivity increases with temperature. And in case of semiconductors, it will be, there is a different phenomena. So if in case of semiconductors at room temperature, you will be having less conductivity. So if you increase the temperature, then more electron hole pair will be, okay, there will be more formation of electron hole pairs. So that is the method of the electric conduction there. So here it is different in metals, that's why it is different relations. Next up, you have which part of optical fiber passes the signal. Your options are cladding, coating, wire and core. So answer will be core. So this is how your optical fiber looks like. So this is the assembly. In innermost part is made of core, and in this part your optical signal is passing, and there is then signal passes through the core. Then after that there is a cladding which constraints light rays to travel within the core, and then there is coating which protects core and cladding from the damage. Next is which material has the highest electric conductivity among these options. So your options are aluminum, silver, copper and steel. So we know that the most wires are made of either copper and aluminum, but that is because they have low cost compared to silver, but silver has the highest electrical conductivity among these. So based on conductivity, solid materials can be classified as conductors, semiconductors and insulators, and this is the conductivity range. So in case of conductors, you have 10 to the power 7 inverse of ohm meter. This is the conductivity. Higher than this, and in semiconductors it will be between 10 to the power minus 6 to 10 to the power 4. For insulators it will be lesser than 10 to the power minus 10. And here from this table also you can see silver has the highest electrical conductivity. After that there's copper, then gold, and among these steel has lowest one. Next up you have piezoelectric effect is analogous to. Options are electrostriction, magnetostriction, anisotropy, or magnetization. So piezoelectric is in case of smart materials it is an effect, so related to that we have magnetostriction. So in case of piezoelectric materials they convert electric energy to mechanical energy and vice versa, and these can be used as actuators which provide a voltage to create motion. Sensors such as many accelerometers and energy harvesters, since the charge generated from motion can be harvested and stored. A ferromagnetic sample changes its length with the application of magnetism, then this type of effect, magnetostriction, in materials arises due to domain migration and reorientation under applied magnetic field H. Now we go through some lecture notes. So firstly you have optical properties. In this we'll talk about lasers and also optical fibers. Then we'll go through also electrical properties, magnetic properties, and also thermal properties. So firstly in optical properties you have this electromagnetic spectrum. So this is the radiation. So these all rays that are here, gamma rays, X-rays, microwaves, radio waves, these all travel through the speed of light, but they have different energies. So energy is the function of your wavelength. So as the wavelength is shorter in this, for gamma rays it will be shorter, and as you moving downwards then it is longer wavelengths, and also frequency is higher in this case, and also energy is higher. So for example gamma rays, these will be will be giving some more damage compared to these waves, and these are, even metals are transparent to these gamma rays. So color wise you can remember, like near ultraviolet you will be having violet color, and near infrared you will be having red color. So if you want to remember the energy, so energy will be higher in case of ultraviolet rays, so you can remember this sense. So violet will be having 3.17 electron volt and red will be having 1.62 electron volt. Now electromagnetic radiation. Each electromagnetic radiation is characterized by a combination of a time varying electric field E and a time varying magnetic field, which propagates at perpendicular to each other, and the direction of propagation is also perpendicular to both of these directions. So it propagates through the space and having a specific range of wavelengths. All electromagnetic radiation traverses in a vacuum at the same velocity, 3 times 10 to the power 8 meter per second, which is the highest speed. Now there are relations, for example for the speed of light c, velocity, and energy. Energy can be given as h, which is Planck's constant, times the nu. So nu is frequency of the radiation. Nu can also be written in terms of wavelength, c upon lambda. So c will become nu times lambda. C will be equals to 1 upon under root epsilon naught and mu naught. Here epsilon naught is electric permittivity of vacuum, which is a constant, and mu naught is also constant. which is magnetic permeability of vacuum, and this C is also constant velocity of light. Now next up you have H, Planck's constant. Its value can be useful, so 6.6 times 10 to the power minus 34 joule second, and this is frequency and wavelength. Next up, in case of light interaction with solids, so there is incident light is reflected, so it can incident then reflect, so from an angle it will change its direction, so this will be used as reflected IR, and it can transmit, it can go through the material. If it's transparent, then more light will go through it, so this is transmitted, and then some part is absorbed, that is absorbed intensity. So incident light is reflected, absorbed, scattered and transmitted. So this incident can be in three parts. Now optical classification of materials, so they can be transparent. So in case of some transparent material, if you make it in terms of single crystal, then you will be seeing completely transparent. If you make it in terms of polycrystalline, then because of the presence of these grain boundaries, you will be seeing it as translucent. And if this polycrystalline material will also have some pores in it, then it will make this opaque. So very less light will be going through this material. Now optical properties of metals. Now all frequencies of visible light are absorbed by metals because of the continuously available empty electron states, which permit electron transitions. The incident radiation having frequencies within the visible range excites electrons into unoccupied energy states above the Fermi level. So here some electrons which are at the lowest energy states, they will get excited and get on the higher levels. Now so the incident radiation is absorbed, hence metals are opaque. The Fermi energy is the maximum energy occupied by an electron at 0 Kelvin, and the change in energy of the electron delta E is equal to the energy of the photon. So the energy of photon will decide how much states this electron will jump to, and the re-emission of the photon of the light takes place by the direct transition of the electron from a high to a low energy state. So this electron can't be in this position for long, so it will again come back. So after come back, this photon will be emitted. So the energy can be different or it can be similar. So the metals are opaque to low frequency radiation such as radio waves to about some middle of ultraviolet rays, and metals are transparent to high frequency such as X-ray and gamma rays radiation. Next is application of optical phenomena such as luminescence. So it is a process where a material absorbs energy and then immediately emits visible radiation. It consists of electron excitation and then dropping down to the lower energy states. If the emission of radiation occurs within 10 to the power minus 8 seconds after excitation, the luminescence is called fluorescence, and if it takes longer than 10 to the power minus 8 seconds, then it is known as phosphorescence. Ordinarily, pure materials do not display this phenomena, but some special materials called phosphates have this capacity, such as BAMgAl10O17, yttria Y2O3, zinc sulfide and cadmium sulfide. Applications are in fluorescent lamps, CRT, cathode ray tube, plasma video display screens and white LEDs. Next is photoconductivity. Now this is different from the earlier conductivity that we studied in case of metals. Now in this case, bombardment of semiconductors by photons with energy equal to greater than the band gap may result in the creation of electron hole pairs that can be used to generate current. Now this process is called photoconductivity, and it is different from photoelectric effect in the sense that an electron hole pair is generated whose energy is related to band gap energy instead of free electron alone whose energy is related to the Fermi levels. The current produced in photoconductivity is directly related to the incident light intensity, and this phenomena is utilized in photographic light metal meters. Cadmium sulfide is commonly used for the detection of visible light, as in light meters. Solar cells are also based on photoconductivity. Next you have lasers. Laser is its acronym for light amplification by stimulated emission of radiation, and unlike luminescence which produces incoherent light, the light produced by laser emission is coherent and constant phase difference and the same frequency. This is based on the fact that in certain materials, electrons excited by a stimulus produce photons, which in turn excite additional photons of incident wavelength. Some of the examples are ruby, which is single crystal of alumina doped with little amount of chromium. Yttrium aluminum garnet, which is also known as YAG, YAG, which is Y3Al5O12 doped with neodymium, Nd. Helium neon laser, some semiconductors like gallium arsenide and indium gallium, gallium arsenic and phosphorus. Now some applications are in welding, metal cutting, heat treatment, surgery and laser surgery of eyes and other, and reading compact discs, etc. Next application you have optical fibers. So this is a medium for carrying information from one point to another in the form of light, and fiber optics is not electrical in nature unlike the copper form of transmission. So it has been calculated that it would require 30,000 kg of copper to transmit the same amount of information as only 0.1 kg of optical fiber material. And the information such as telephone conversation in electric form is first digitized and into bits, that is ones and zeros, and this is accomplished in the encoder, and then the electrical signal is converted into an optical photonic using the electrical to optical converter, which is normally a semiconductor laser. Then this laser is emitted in monochromatic or coherent light infrared region. Low absorption, it causes low absorption losses. The output converter is in the form of pulses of light, a binary 1 which will be having high power pulse and 0 having low power pulse. The pulse signal are then fed into and carried through the fiber optical cable. At receiving end, reverse process takes place. Receiving end. So this is the simpler form of the previous one that I earlier told. So this is the components of optical fiber. Inside you have core having 8 micron to 62 micron dia. Then you have cladding having 125 micron outer dia. Then you have coating up to 250 micron to 900 micron. So it is very compact compared to some other assemblies. So then you have core, cladding and coating. Core you'll be using to pass the signal to the core, then cladding will be constraining the signal inside by total refraction, then coating which will be protecting core and cladding from the damage. So first you have encoder, then you have this will convert your electrical to the optical signal, then you have this fiber, optical fiber cable, and in between you have repeaters, then you have again optical to electrical signal converter, then this signal will be decoded. Now applications of these optical fibers. So these experiences geometrical size and shape and optical changes such as reflective index and mode conversion depending upon the nature and the magnitude of the perturbation. So the optical fiber serves as transducer and converts measurements like temperature, stress, strain, rotation and electric and magnetic currents into a corresponding change in the optical radiation. So since light is characterized by intensity, phase, frequency and polarization, any one or more of these parameters may undergo a change. In case of intrinsic sensors, you use the fiber itself as the transducer. So in this case, your light is going and coming out, and in between you have some parameter of interest. So based on this, there might be change in the signal. And in case of extrinsic sensor, you use fiber to supply light only to a sensing device and then return signal light to a detection system. So there will be another external transducer which will be sensing this change. Next up we have thermal properties. So in this case, thermal properties describe the response of material to application of heat. So as a solid absorbs energy in the form of heat, its temperature rises and its dimensions increase. And some of the important thermal properties are heat capacity, thermal expansion and thermal conductivity. Polymers have significantly large Cp because covalent bonds in polymer do not let atoms exchange electrons as metallic bonds do. So here we can see Cp values are higher for polymers, 900, 1900, 1800 and so. And in case of ceramics you have lower Cp values, and for metals you have somewhat similar to ceramics. Heat capacity, so it represents the amount of energy that is required to produce a unit temperature rise. So you want to increase 1 degree Celsius to a certain material, so how much energy is required to do that, and it is indicative of a material's ability to absorb heat from the external surroundings. So mathematically you can say heat capacity as energy change, gain or loss divided by resulting temperature change, unit temperature. So dQ upon dt will be your Cp. And heat capacity, so it increases with temperature. So here also you can see heat capacities keep on increasing with temperature and it will be 0 at 0 Kelvin. And for solid, it reaches a limiting value of 3R. R is your gas constant. And from an atomic perspective, energy is stored as atomic vibrations, and as temperature increases, the average energy of atomic vibrations increases. Next you have thermal expansion. So temperature of a solid is a measure of its potential energy, and most solid materials expand upon heating and contract on cooling. Heating to successively higher temperatures raises the vibrational energy, thus the interatomic separation increases from R0 to R1, R1 to R2 and so on. So here this curve will keep on shifting if you keep applying some temperature. So the greater the atomic bonding energy, the deeper and narrower this potential energy trough will be. Thus, the increase in the interatomic separation with a given rise in temperature will be lower. So for metals and polymers, in case of polymers, these will have highest of alpha values, alpha thermal expansion, and lowest will be for ceramics. So it depends on the type of bonding. Next up you have thermal conductivity. So in case of thermal conduction, you have so in case of thermal conduction is phenomena by which heat is transported from high to low temperature regions of a substance. And Fourier law states that for a steady state, the heat flux is directly proportional to a temperature gradient. So Q upon A will be equals to minus K times dt upon dx. K will be your thermal conductivity in watts per meter Kelvin. And if you have negative sign, which will be indicating that heat flows in the direction of decreasing temperature. And thermal conduction in a solid takes place by both lattice vibration waves known as phonons and free electrons. Thus total conductivity is K equals to K because of L lattice vibrations and K because of electrons. Next up, in metals are extremely good conductors of heat because relatively large numbers of free electrons exist that participate in thermal conduction. The purest form of metal will have high conductivity than the alloy form, because your electron will interact with the alloying elements. So in the alloy, different atoms will have different electron affinity. Thus movement of excited electron becomes hard. Since free electrons are responsible for both thermal and electrical conduction in pure metals, the two conductivities are related by Widman-Franz law as L equals to K upon sigma T. Here L will be Lorentz constant and K will be thermal conductivity, sigma will be your electrical conductivity, capital T will be absolute temperature, meaning in Kelvin. Now for various materials, these are the thermal conductivities. For silver it is 410 and for steel it is around 52. For copper it is around 385. So it is highest for silver followed by copper. Next we have ceramics. So these are thermal insulators as they lack large number of free electrons. Thus the phonons are primarily responsible for thermal conduction. So Ke is lesser than Kl in this case. Also the phonons are not as effective as free electrons in the transport of heat energy due to phonon scattering by lattice imperfections. The room temperature thermal conductivities range between approximately 2 to 50 watts per meter Kelvin. Amorphous ceramics have lower conductivities than crystalline ceramics as the atomic structure is highly disordered and irregular. Higher porosity also reduces conductivity due to the presence of still air. So because air has low conductivity, 0.02 watts per meter Kelvin in form of pores. Next we have polymers. So in this case the thermal conductivities for most polymers are of the order of 0.3 watt per meter Kelvin, and energy transfer is accomplished by the vibration and rotation of the chain molecules, and magnitude of the thermal conductivity depends on the degree of crystallinity. So the highly crystalline and ordered structure means effectively coordinated vibration, higher thermal conductivity. Now for various materials, in this case for metals, aluminum, steel, tungsten and gold, these are the thermal conductivities. So it is highest for gold here among these four, it is 315. In this case your atomic vibrations and motion of free electrons both contribute to the thermal conductivity. In case of ceramics, magnesia, alumina, soda lime glass, silica, these have lower thermal conductivities, lowest for silica. In this case you have atomic vibrations contribution only. Then you have polymers such as polypropylene, polyethylene, polystyrene and Teflon, which have thermal conductivities in 0.12, 0.46, 0.13, 0.25, and in this case vibration or rotation of chain molecules will be contributing to the thermal conductivity. Next we have thermal stresses and shock. So in this case thermal stresses are stresses induced in a body when due to changes in the temperature the deformation is hindered, and thermal stresses in a constrained body will be of compressive nature if it is heated and vice versa. Thermal shock, if the dimensional change in a material are not uniform, that may lead to the fracture of brittle materials like ceramics, which is known as thermal shock. The capacity of a material to withstand thermal shock is defined as thermal shock resistance. So it can be given as approximately sigma F times K divided by E upon alpha. So thus for high thermal shock resistance, a low value of thermal expansion coefficient alpha and elastic modulus E is desired, and a high value of thermal conductivity K and fracture strength sigma F is desired. Next up we have electric properties. So in this case we have Ohm's law. V voltage is equals to current times the resistance. So here V is voltage drop, volts, I is current in ampere, R is resistance of material in ohms. So R is the proportionality constant here, so V proportional to current. Material's electric resistance is an extrinsic property, which means it depends on object geometry, and the resistivity is independent of specimen geometry, which is an intrinsic property but related to R through the expression R equal to rho times the L upon A. A will be your cross section of the conductor. Here L is distance between voltage measuring points. A is cross sectional area perpendicular to the direction of current. Unit of rho will be ohm meter. So this is your resistor which is connected to the battery, and here your this is where you are measuring your voltage across, and you are measuring your current as well. Next up you have electrical conductivity. In case of electrical conductivity is indicative of the ease with which material is capable of conducting an electric current, and electric conductivity is given as sigma equal to 1 upon rho. So units will be inverse of ohm meter. So on the basis of conductivity, solid materials can be classified as conductors, semiconductors and insulators. Insulators will be having lowest conductivity. Electronic and ionic conduction. Now in case of electronic conduction, you have current arising from the flow of electrons, while in case of ionic conduction you have current arising from net motion of charged ions. Next you have these we already talked for metals, and in case of graphite you have high conductivity, lesser than metals though, but it's still higher. In other ceramics you have very less conductivity, and in polymers as well, they ceramics and polymers both they act as electric insulators. Next you have effect of temperature on metal conductivity. So as in this graph you can see, with increasing temperature your electrical resistivity increases, so conductivity will reduce, and also with increasing amount of some alloying element you can see your resistivity is increasing. And increasing temperature causes greater electron scattering due to increased thermal vibration of atoms. Hence the resistivity of metal increases or conductivity decreases linearly with temperature. The total resistivity of a metal is the sum of the contribution from the thermal vibrations or impurities and plastic deformation. So scattering mechanisms act independently on one another. In case of insulators you have wide band gap, more than 2 electron volt. So if you increase the temperature, very few electrons they get excited and cross the band gap. In case of semiconductors they have narrow band gap, less than 2 electron volts, so more electrons get excited and cross the band gap. So for semiconductors your resistivity will decrease with increasing temperature. Next we have magnetic properties. This is the last topic. So in this case the magnetic field is a force which is generated due to energy change in volume of space. So a magnetic field is produced by an electrical charge in motion, for example current flowing in a conductor and orbital movement and spin of electrons. So because of this spin and as well as this orbital motion, there will be some magnetic field generated. So origin of magnetic moment, it is orbital motion around the nucleus. Electron is considered to be a small current loop generating a very small magnetic field having a current magnetic moment along its axis of rotation. Next you have spin of electrons. So the spin of electrons also produces a magnetic moment along the spin axis, and spin magnetic moments may be only parallel or anti-parallel. Next we have diamagnetism. So it is a weak form of magnetism which arises only when an external field is applied, and it arises due to a change in the orbital motion of electrons on the application of a magnetic field. And there are no magnetic dipoles in the absence of a magnetic field, and when a magnetic field is applied the dipole moments are aligned opposite to the field direction, and the magnetic susceptibility chi m will be equals to m upon h, where m is magnetization, h is the field intensity. So it is negative, which means B, magnetic flux density in a diamagnetic material is less than that of vacuum and is repelled by the applied magnetic field. And magnetic materials such as alumina, copper, gold, silicon, zinc are some examples. Now in absence of some outer external magnetic field, there won't be any domains or alignment, and as soon as you apply some magnetic moment, this will This will oppose this in opposite direction. Next up we have paramagnetism. So in this, the cancellation of magnetic moments occurs between electron pairs is incomplete, and hence magnetic moments exist without any external magnetic field. However, the magnetic moments are randomly aligned, hence no net magnetization without any external field. When a magnetic field is applied, all the dipole moments are aligned in the direction of the field, and the magnetic susceptibility is small but positive, which means B is a paramagnetic material is slightly greater than that of a vacuum. And examples of paramagnetic materials is aluminum, chromium, molybdenum, titanium and zirconium. So in absence of any external magnetic field, you have randomly oriented domains, and as soon as you apply some magnetic field, it will get magnetized. So in case of ferromagnets, if you heat your material up to Curie temperature, after that this will show paramagnetism in that material. Next up we have ferromagnetism. So certain materials possess permanent magnetic moment in the absence of an external magnetic field, which is known as ferromagnetism. Now permanent magnetic moments arise due to the uncancelled electron spins by virtue of their electron structure. So when you so the coupling interaction of electron spins of adjacent atoms, they cause alignment of moments with one another, and the origin of this coupling is attributed to the electron structure. So this D block, it won't be entirely filled and some unpaired electrons will be there, so this will lead to formation of this type of ferromagnetism. For example, in case of iron, which has 26 atomic number, so it has argon type of structure, and after that it has 4s2 and 3d6. So these in case of D block you have 5, so out of those you have 4 unpaired electrons. So it has incompletely filled d orbitals and hence unpaired electron spins. So even in absence of some external magnetic field, you will be having these aligned domains. Next up you have antiferromagnetism. So if the coupling of electron spins result in an anti-parallel alignment, then spins will cancel each other and no net magnetic moment will arise. This is known as antiferromagnetism. Manganese oxide is the example. So in manganese oxide, O2 minus ions have no net magnetic moments, and the spin moments of Mn2 plus ions are aligned anti-parallel to each other in adjacent atoms. Next up we have perimagnetism. So certain ionic solids having a general formula M Fe2O4, where M is any metal, show permanent magnetism, termed perimagnetism due to the partial cancellation of spin moments. In Fe3O4, Fe ions can exist in both 2 plus and 3 plus states as Fe2 plus O2 minus, or Fe3 plus O2 and O2 minus 3 in 1:2 ratio. Now the anti-parallel coupling between Fe3 plus, half in A sites and half in B moments, they cancel each other, and Fe2 plus moments are aligned in the same direction and result in the net magnetic moment. So this will have a magnetic field weaker compared to ferromagnets. temperature influence of on magnetic behavior. So the atomic vibration increases with increasing temperature, and this leads to the misalignment of the magnetic moments as they are free to rotate. Above a certain temperature, all the moments are misaligned and the magnetism is lost. The temperature is known as Curie temperature, Tc. So here below Tc you can see there is some orientation and some alignment in domains, but above Tc this is completely lost, and this saturation magnetism also keeps on decreasing with increasing temperature. So above a certain temperature all the moments are misaligned. The magnitude of the Curie temperature varies from material to material. For example, iron has 768 degrees Celsius, cobalt has 1112 degrees Celsius, and nickel has 335 degrees Celsius, and this Fe3O4 has 585 degrees Celsius. Now, ferromagnetic materials exhibit small volume regions in which magnetic moments are aligned in the same direction. These regions are called domains, and adjacent domains are separated by domain boundaries, and the direction of magnetization changes across the boundaries. The magnitude of magnetization in the material is the vector sum of the magnetization of all the domains. Now here also you can see these are the domains and these are the domain walls. Next, magnets can be classified into two categories. First is soft and hard magnets. So this is based on the applications as well as their properties. So energy product kilojoule per meter cube. This is the area of the largest pH rectangle that can be constructed within the second quadrant. So in this area, this is the first quadrant, second, third and fourth quadrant. So in this quadrant you find out the biggest possible rectangle. So area of the largest pH rectangle that can be constructed within the second quadrant of the hysteresis curve. So this represents energy required to demagnetize a permanent magnet, and large pH max, if some material has this large pH product, then it will be harder is the material in terms of its magnetic characteristics. So if this hysteresis curve that I showed earlier, now this, if this is area of this is narrow, then it will be soft magnet. So narrow hysteresis curve will be for soft magnets, broad hysteresis curve will be for hard magnets. In case of soft magnets, you have high initial permeability and low coercivity and easy movement of domain walls. And it also has easy to magnetize and demagnetize. Examples are iron silicon alloys, nickel iron alloy and iron. It is used widely in generators, transformers and switching circuits. In case of hard magnets, you have broad hysteresis curve, you have low initial permeability, high hysteresis energy losses and high coercivity, and it is difficult to demagnetize. Now examples are alnico, which is alloy of aluminum, nickel and cobalt, and ferrites, rare earth cobalt, platinum, etc. Hard magnets are used in all permanent magnets in applications such as power drills, motors and speakers. Now this is the hysteresis loop. So here you keep on changing the applied magnetic field and measure what is the magnetization inside the material. So your magnetization is on y-axis. So as you keep on changing the applied field, you will see change in magnetization. So this is completely magnetized here at this point, and then it shows reduction in magnetization. So some of these arrows, these will get in different direction. So this will keep on reducing, and this will go at 0, but there will be some magnetization. Even if you keep the value here, even if the value of this applied magnetic field is 0, but there is still some magnetization in the material. Okay, now this is termed as the remanence. So a measure of remaining magnetization when the driving field is dropped to 0. Now as you keep on decreasing this magnetic field, you will be even in negative, then you will be finding at a point that you will be having this magnetization as 0. This is the coercivity. So this is a measure of reverse field that is needed to drive the magnetization to 0 after being saturated. Now then you keep on applying this magnetic field in negative, then you will again find the complete magnetization, which is the saturation. So all domains will align in one direction, and then you will be getting saturation, and after that you keep on increasing this magnetic field in positive direction, then you will again reach to this direction. Okay, so based on this hysteresis loop, we can tell whether a magnet is soft magnet or hard magnet, and we can find out the BH product as well, which will give you energy product. Okay, so that's it from my side.